Hi, this will be a presentation of the Laboratory of Vibration and Acoustics, a research unit within the National Institute of Applied Sciences from Lyon, France. My name is Goran Pavic. The red dot on the map shows our position. One can clearly see that not only we are about 7 miles away from the center of the world, but also we are at about 2.5 miles distance from the headquarters of Interpol, the International Criminal Police Organization. So watch out. Our mother institution, INSA, is an engineering school, medium-sized in terms of number of students and staff. There are 12 departments. One of these is the mechanical engineering department to which we belong regarding the teaching. 21 research units, which we call laboratories, and about 660 teaching and research staff for about 5,400 students, out of which about 600 PhD students. Our laboratory, LVA, has a team of 20 permanent staff members, out of which 16 researchers, about 30 PhD students and postdoc fellows. We get our money from the Ministry of Higher Education and Research, then from collaborative projects and from industrial contracts. When we have some free time at work, we spend it mostly on 4 research areas. Vibroacoustics, focused at modeling of sound and vibration of mechanical and fluid origin. Then identification, with the objective of finding out the acoustical and mechanical properties of sources, components, and materials. Then subjective perception of noise and vibration, where we study discomfort and annoyance caused by noise and vibration on humans. And monitoring diagnostics and non-destructive testing, involving condition monitoring of machinery, mostly rotating machinery, identification or location of defects using sound and vibration signals, and scan of mechanical components by guided ultrasound waves. Our teaching is carried out within the Department of Mechanical Engineering, while the research is done in our laboratory, seen in the front of this large building. On the right, there is located a key research tool, the coffee machine, which is why this area is called the main area. When we wish to be left on our own, we can choose one of the shelters you can see on this page. Among these, there is a large reverberation chamber, mostly used for the work on sound transmission through lightweight structures. Then a large semi-anechoic chamber. Not sure what we do there. Most probably the work which has to be done in a large semi-anechoic chamber. And a number of other specialized facilities, some of which are shown here. And that's it. To give you some idea about what we spend our time on, I will shortly present 3 typical research subjects which seem to represent some potential for real-world applications. One of them is noise transmission through elastic structures induced by turbulent boundary layer. Second topic is dynamic behavior of multi-layer anisotropic composite panels. And finally, the airborne source characterization in realistic measurement conditions. So let's start with the turbulent boundary layer noise excitation. The applications are many. All the vehicles like aircraft, cars, ships, but also the ducts made of thin sheets, etc., are sensitive to the noise created by boundary layer in turbulence. If we wish to measure literally the noise transmission under TBL excitation, we need to have expensive facilities like a wind tunnel, but also we are faced then with delicate reproducibility issues because it is not very easy to maintain well-controlled excitation conditions. So the challenge is to create the TBL pressure conditions using a controlled sound excitation. The good news is that there exist a number of TBL models like those of Korkos, Chekhov, Goody, Rosenberg, Smalyakov, etc., which can help. The question is about can we use some of the existing facilities for the measurement of transmission loss to come close to the conditions of turbulent boundary layer excitation. Here, a layout of such a facility in our lab. A number of other labs have similar facilities. We have here a reverberation chamber to create a diffuse sound field, an anechoic space on the other side to pick up the sound power transmitted through the tested specimen, which is here. All looks pretty decent for a moment, but if we look at the map of a diffuse field here and the TBL created field here, we see that not only we have differences in levels, but also the differences in the spatial structure of the two fields, as it has been shown by Maury and the co-authors some almost 20 years ago. So the answer to this question is no, we cannot use standard facilities for the measurement of turbulent boundary layer noise. The idea is to recreate the excitation similar to the one created by the turbulent boundary layer, but using an array of loudspeakers. The technique originally developed by a colleague, Laurent Maxit, was the following one. First, reconstruct the desired TBL pressure here from the model used. Since the model is of a statistical nature, the procedure has to be repeated many times and the results subsequently ensemble averaged. Then identify by measurement the transfer functions between the sound pressure responses measured by microphones at a rigid baffle, the size of which corresponds to the targeted panel, and the sound excitation at the positions of the loudspeaker array. Then compute by inversion the source strength needed to reproduce the modeled TBL pressure. Finally, using the loudspeakers, the strength of which has been already defined in step 2, we apply the sound to the target panel and measure its response. The drawback of this technique is that too large number of sources is needed in order to reproduce fine detail required by the TBL pressure spatial resolution. So another solution had to be found. So a new technique was put in place by analogy with the procedure of improving the resolution of underwater sonar scanning. It turns out that the larger the source array size, the better the spatial resolution. The array size can be artificially increased by combining the signals at different times to account for the effect of the increased array geometry. It is called the synthetic aperture array. The new procedure starts with the modeling of the TBL pressure, just as the original procedure, but then uses the transfer functions obtained by the synthetic array. A line array of microphones embedded in a rigid baffle and a single point source is all what is needed. The source is simply a nozzle connected via a hose to a compression chamber actuator. Then the step 2 here is to use the microphone array to characterize the source for each position. Once this is done, the step 3 is to characterize the response of the panel. And finally, the step 4 is to synthesize the panel response under the TBL excitation using the target pressure obtained in step 1. The new technique was validated in different ways. First, since the computation is done at each frequency in a 2D wave number space, a check was made about how well the synthetic array reproduces the originally defined TBL pressure. Here an example showing one of the two wave number components, the component Kx in a lengthwise direction. The top map here is the original pressure. The bottom one is the pressure reconstructed using the synthetic array. The matching looks fairly decent. At low frequencies, the matching suffers due to the long wavelength effect. The ultimate validation was done by comparing the vibration velocity of a simply supported AL plate, which was directly measured in the wind tunnel of the University of Sherbrooke, and then computed at our lab by the technique shown previously. Here is the plot of the spectra in terms of the power spectral density of the plate vibration velocity. Black line is the synthetic array result, and the red line is direct measurements in anechoic chamber of the University of Sherbrooke. You see that the matching is pretty good, which is even more remarkable when one takes into account all the hypotheses pulled in the modeling procedure. We now switch to the second subject, the anisotropic multilayer panel. The importance of this type of structural components is fairly well known. In order to optimize a multilayer design, one needs modeling. Numerical modeling requires a fine mesh and can be excessively time-consuming, thus a need for analytical models. Here are some examples of such models. A homogeneous model, with a simplified distribution of displacement across the thickness. It is simple and inaccurate. Then a heterogeneous one, with each layer treated on its own, and the compatibility conditions applied at the interfaces. This one is accurate but very difficult to handle. Finally, a compromise solution, a zigzag model with each layer of Reasoner-Mindlin type, with all the variables expressed in terms of variables of the bottom layer. Such an approach is used here to apply it to the case of multi-layer anisotropic panels, producing as a result an equivalent Love-Kirchhoff plate of frequency-dependent coefficients. An initial validation of the analytical model was done by comparing it with a numerical computation using the spectral finite elements applied to an isotropic sandwich panel. The numerical model produces 6 different types of waves, which are all shown here. The analytical model reproduces 5 of these 6 types to a high degree of accuracy. We see excellent matching between the spectral finite element results and those obtained by the analytical modeling. The 6th wave type, which is of lesser practical importance for noise, concerns layer deformation across the thickness, which are supposed not to exist in Reasoner-Mindlin hypothesis. This is why we can't have in analytical formulation this 6th wave. So far, so good. Here an example of a multi-layer carbon composite sheet, fairly thin, where the layers had different orientations, shown here. The measurements done by a scanning laser vibrometer enabled the mapping of the normal vibration and its representation in the 2D wave number space. The black line represents the condensed model, orthotropic model of the entire sheet, where the flexural wave number is given by 5 equivalent dynamic parameters. The identification was done using the so-called inhomogeneous wave correlation technique. Since the sheet was fairly thin, there was no appreciable variation of elasticity with frequency. But the next slide, the next figure will show this. Here we have a sandwich made of very thin carbon layers and spruce core. And here we see the 5 orthotropic elasticity parameters, which now considerably vary with frequency as the thickness of the core was fairly large. There is a clearly visible here the transition zone, which delimits the range of low frequencies where the sandwich behaves as a solid panel here, and the range of high frequencies where the carbon sheets behave as uncoupled to the core, which in return drastically reduces the dynamical panel stiffness. Such a behavior was already found on isotropic sandwiches by Nilsson in the 80s. Finally, a few words about the structural damping of multilayer panels. Here we have a case of flexural vibration of an isotropic sandwich with a polymer core between two metal sheets. The plot shows the loss factor versus frequency. The two full lines correspond two ways of getting the loss factor by modeling. The red curve here is obtained from the equivalent definition, taking the groove velocity as double the phase velocity, which is valid for a Kirchhoff plate, but not for this one. The blue line here, obtained by the correctly identified group and phase velocities of flexural waves from the model, is seen to match far better the scattered points, which represents measurement data obtained by 4 different techniques, 2 of which are identified here. So, looking from the damping viewpoint, the presented multi-layer modeling seems to work rather well. And now our last subject, the characterization of a source of airborne noise. The objectives can be different. For example, the assessment of the contribution of different source parts to global noise, or the prediction of noise by the source installed in a given space, or even validation of noise computation procedures. Now, the subjects looks trivial until you try to do it. In fact, the correct characterization is fairly difficult. Here, the example of an IC car engine. The difficulties are reflections from the surroundings, noise from sources other than the engine itself, notably the brakes needed to load the engine, effects of obstacles like, for example, engine supports here, which are placed within the measurement volume. Our lab has developed different characterization procedures, and one of these, the IPTF, standing for inverse patch transfer function, is a field reconstruction method using the concept of virtual acoustic volume surrounding the source. So we have here a source like an engine, and around we shall define an acoustical volume by means of which the characterization will be made. The technique combines numerical modeling of the virtual volume and measurements of sound on and within this virtual volume. The boundary conditions of the virtual volume can be selected according to the available sensors. For example, if we have microphones only, this corresponds to free boundary. If we have the PU probes, which involve both measurement of pressure and particle velocity, then we can have blocked boundaries. The presence of obstacles like mounting frames is taken into account in the numerical model of the volume. The sound field can be reconstructed across any surface comprising the real source surface. So we can have on the source surface the completely defined sound field in terms of sound pressure and particle velocity normal to the surface. The reconstruction process is independent of the acoustic conditions exterior to the virtual volume. at least theoretically. The validation of the source characterization method using the IPTF technique was done in several ways. Here we see the comparison of the pressure fields in 2 points of the virtual volume obtained directly using the reference calculation by the Nastran and Actron codes, and computing using the concept of virtual acoustic volume and the 2 direct formulations of the IPTF methods. A very good matching is seen, which validates the principle built in the approach. For this computation, the IPT technique was using 862 patches for the oil pan. The virtual volume was characterized by 576 patches, while the numerical model had a number of elements close to infinity, as usual. Here we see the field of sound intensity at 1 kHz emitted by the entire engine here on the left and only by the oil pan on the right. We see the results obtained by the IPTF and by numeric computation. Here too, IPTF and numeric. To make the numeric computation possible, the engine was excited by shaker in order to avoid possible errors in modeling the engine excitation. We see that in spite of inevitable discrepancies, the qualitative matching is fairly reasonable. This plot shows the correlation between the IPTF and numerical computation. The correlation is expressed via the so-called RVAC criterion, which is such that no correlation is 0 and perfect correlation is 1, just for a coherence function. The 3 curves shown here correspond to 3 components of the engine: cylinder head cover, oil pan, and valve timing cover. As one can see, the correlation looks fairly decent. What you see here is not a parrot, but an engine. Different components are indicated by different colors. On the right, we see the patches used in the procedure. The chart below shows the contribution to noise of different components in 1/3 octave bands. So one of the useful results which we can obtain by the IPTF is the ranking of different components of a complex source in terms of the acoustical power radiated by the source. So this brings us to the thank you for your attention page. I hope that those listening to this presentation feel now much better than at the beginning. Should you have any questions, do drop us a message at the email address shown here. And keep safe. Bye.